Welcome back to section 3 of chapter 6. In this section, we're going to expand on the exponential functions that we saw in the last section and look at exponential growth and decay. I did mention in the last section that exponential growth is when it grows kind of like that one, and exponential decay is when it's backwards and it's going this direction. But we're going to look more into that. We're going to see rates of change and a bunch of fun stuff like that. Now, the last one had a bunch of stuff that really was kind of mental math. Like we had 2 to a power, we had 1/2 to a power, we had 3 to a power, stuff like that. That's not going to really be the case here. You're going to want to have a calculator with you that is capable of handling exponents. If you don't have a calculator with you, you can always just pull up Desmos and plug it right into the graph and it shows you where it is, or it shows you the answer. I've got a couple illustrations of that throughout the lesson today. So, our learning target: I can use exponential functions to model situations and make predictions. So our first step is exponential growth. We're going to get problems. Say something like the population of Hillville grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? And it gives us an initial condition, and it gives us a rate of growth. We have the annual rate of 15%. Now that's different than what we saw last time. Last time it would be it doubles or it triples. So how do we grow by 15%? Well, let's look at our equation, our exponential equation. F of x equals a times b to the x. And that's great when it doubles or something. But to grow by 15%, we're going to kind of split that b up into 2 different pieces. That b is going to be 1 plus the rate. Now the rate needs to be written as a decimal. So our population here, I'm going to go p of t, so population for time t, you can change it. It doesn't have to be f of x. P of t is going to equal the initial condition, that's at 5,000, times 1 plus 0.15, because that's 15% as a decimal, all to the t. So we could rewrite this: P of t equals 5,000 times 1.15 to the t. Now what's important is you cannot multiply the 5,000 times the 1.15 because the exponent has to come first. It's the exponent and then you multiply. So we want to find what will the estimated population of Hillville be in 5 years. So we're going to plug in 5 for t. Population at 5 will equal 5,000 times 1.15 to the 5. The very first piece of this that we do is we do the 1.15 to the 5, which, being that it's in your calculator, you don't actually have to write the step out. So 1.15 to the 5th power should be about 2.001 or 2.011-ish. So if you're following along, you don't know if you're doing it right, check, make sure you should get about 2.011. And then we're going to multiply by 5,000. I am not going to write this number down and retype it into my calculator. I'm going to go times, and it's going to say, hey, I'm taking the answer times 5,000. If you're doing it in Desmos, you can just type it out exactly as it shows. And what we get is 10056.7859, so 0.786. So that's what we get for the equation. Now we do have to use some sense here. So we're finding what is the estimated population of Hillville in 5 years? Well, we're not going to have 0.786 people. We need to round this to a whole number. Like certain things, like if you're looking at the number of things, you're not going to have decimals. So this is going to round up. So we should have about 10,057 people in 5 years. And so this was largely the same stuff that we were doing in the last section. We just had to set it up slightly differently because we didn't have a times 2. We had to figure out it was 1 plus 0.15. So that would be a simple increase or simple interest. We also have something called compound interest. Now, compound interest you get a lot with bank accounts and stuff because it will not give you your interest once a year. It'll compound it or give you your interest a couple times a year. And so what would happen, let's say we started out with $100 and we had 2% or 4% interest, but quarterly. So it happens 4 times. We're going to get 1% 4 times a year. So we started out with $100, then we get 1%, so that's $101. And then the next quarter, we get 1% of that $101. And then we get 1% of that. So it increases quicker. If we just got the 4% at the end of the year, we'd end up with $104. And so the compounding is good. And the more times per year it compounds, the faster it'll grow. So our equation for this is very similar to what we started out with. Remember, we had f of x equals a times 1 plus r to the t, or to the x, since that's our variable here. Well, what we do, the a, this is still the ending amount. The p is still the initial amount. We use p because it's called the principal when we're talking about money. All right, the r is still the rate, but that's a yearly rate. The n, which happens 2 places, is the number of times per year it's compounded. So if it's compounded quarterly, that would be 4 times per year, so n would equal 4. If it's compounded monthly, n would equal 12. And that goes in both places. We have to divide the rate by that amount, but then we also multiply it to the number of years to find out how many times it actually gets compounded. So what could these look like? We have Kimberly's family invested in a certificate of deposit, it's a CD, for her when she was born. The interest is compounded quarterly. So this tells us n equals 4. What is the value of the CD at the end of 5 years? And then we have the amount deposited, that's the initial amount, that's P. Our interest, R equals 0.08, because 8% is 0.08. So let's plug this in. We have A equals 3,000 times 1 plus 0.08 over 4 to the 4 times t. We're looking at it for 5 years. I'm going to put 4 times t just so that we have the equation. Like this is the equation that we would have. Now we'll plug in 5. So a equals 3,000 times 0.08 divided by 4 is going to be 0.02. So we have 1.02 to the 4 times 5. 4 times 5 is 20. And then, so we go 1.02 to the 20th. See why you would want a calculator for this stuff? Like, this is not something you're going to do in your head. Then times 3,000 is 4,457.842 blah 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 0.84 because it's money. So at the end of 5 years, it'll be worth $4,457.84. So it is earned in 5 years. It's earned $1,457.84. And then will the value of Kimberly's CD be greater after 15 years if it is compounded annually rather than quarterly? And the answer is no. Quarterly will make it get bigger faster. We could find that. We could find it after 15 years, but let's find it annually just after 5 years so that we can compare it to the value that we just found. So if it's annually, n would equal 1, so we have a equals 3,000 times 1 plus 0.08, so 1.08 to the 5th. And so we can go 1.08 to the 5th is 1.46 times 3,000. And this would give us $4,407.98. So even after 5 years, it's increased. Well, we could find it after 15 years really quick. So 1.02 to the 60 times 3,000. So after 15 years quarterly, it would be worth $9,843.09. Annually, it would be worth $9,516.51. So it's getting more and more significant the longer we go out. And so the more times it's compounded, the larger that n value is, the faster it'll grow. Exponential decay. Exponential decay is similar to exponential growth, except instead of getting bigger, it's going to be getting smaller. So we could have, a video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. In how many days total will the video stop being a fan favorite? So we have an initial value. That would be the 8,192 views. And it decreases by 25%. Growth, it would increase by something. Decay, it decreases. Well, what would that do to our equation? It's almost the same, except with a decrease, instead of plus the rate, we're going to subtract the rate. So it's 1 minus r. So filling this one out, the number of views, we go view of time t, is going to equal the initial amount, 8,192, times 1 minus 0.25 to the t. So v of t equals 8,192 times 0.75 to the T. Now it's asking how many days total will the video stop being a fan favorite. So how many until it falls below that 1,000 views? Now it looks like if you're looking at this graph here, that hits at about 6. However, this graph isn't particularly accurate. So we can't trust that. We could do a few different things. We could graph it and look. We can just kind of start plugging in numbers. It's like, all right, so after 4, no, after 5. But a quicker way of plugging in numbers is to make a table. Like use a graphing calculator or Desmos to make a table. And so again, I use Desmos just because that's what everybody has access to. Just desmos.com, click the big green graphing calculator button. To make a table, you'd go to that plus sign and it gives you an option of making a table. You would choose that. We put X up here, put our equation over here, and then fill out the values of X. I just put 1 through 10. And then it automatically found these values. So we want to know when it gets below 1,000. 1,000 would be right here. So on the 8th day, it will stop being a fan favorite. Is there a way to solve that algebraically? Yes, there is, but we don't know how to do that. Not yet. So that'll come later on, significantly later on. Right now we just use graphs, we use tables, and we can find that it's that 8th day that it gets below 1,000. We can use exponential decay to help us solve problems. So here we have number of pica in a region is decreasing. How does the decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? So we're going to find the average rate. So we're basically going to find a slope. So we have an initial population of 144 picas, and it's decreasing at 8% each year. So the pica population, P of t, is going to equal our initial 144 times 1 minus 0.08 to the t, which is 144 times 0.92 to the t. We're going to find a few values here. We need to find the population at years 1 and 5. So P of 1, you just plug 1 in for t. So 0.92 to the 1 is 0.92 times 144 is about 132. Yeah, there's some decimals in there and stuff, but we can round it. And then P of 5, because that's going to be the end of this time period, you plug in 5. So 0.92 to the 5th times 144, you get 95. And to find the average rate of change over these years, we're going to find the slope here. So we're going to go 95, it's y minus y. So 95 minus 132 over 5 minus 1. And when we do that, we get negative 37 over 4, which is negative 9.25. So the population is decreasing by about negative 9.25 pica per year during those years. And now we can do the same thing for years 6 to 10. Population of year 6, we plug 6 in, and we get 87. Population of year 10, plug 10 in, and we get 63. So we can go 63 minus 87 over 10 minus 6 to give us negative 24 over 4, which is negative 6. So it would be decreasing at negative 6 pica per year. So in years 1 through 5, it's decreasing faster than in years 6 through 10, which if you think about the graph of a exponential decay function, it looks like this. So what we just saw is that it's steeper here than it is here. That's what that's showing. But we can find the average rate per year by just finding out how many were on each year and then dividing, finding the slope. One more. Rich is comparing the cost of maintaining his car with the depreciating value of the car. When will the cost and the value be the same? So what is this saying? So the value, the car costs a certain amount when you buy it, but as it gets older, it's not worth as much. And then, but as it gets older, the cost to keep fixing it is increasing. So he wants to know what that middle point is. So we're going to find two different equations here. We're going to find one on the value. So it starts at 20,000 and it decreases by 15% per year. So his value is 20,000 times 1 minus 0.15 to the t times 0.85 to the t. The maintenance, it's 500 in the beginning, and then it's increasing by 28%. So maintenance of year t, we have our initial amount was 500, and then 1 plus 0.28 to the t. So the maintenance is 500 times 1.28 to the t. Now there are ways of solving these algebraically, but again, we don't know what those are at this point. And so what we can do is we can graph both of these. Because we have a system of equations. We just got done with the chapter on system of equations. So we graph them, and we're looking for that intersection point. And so that intersection point, that solution, looks like it's at about 9 years, right? Because it's right about here, so it's about 9 years. And the cost looks like they're both about $4,500. You can always check it. You could plug 9 into both of them to see if you get about 4,500, or maybe even get a little bit more accurate of an estimate there. But this is when they would be the same. So that's exponential growth and decay. Again, it's not much different than what we were doing last section. It's just some application of those skills. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.